So, good afternoon, everyone. In this particular video, we talk about a conceptual question that showed up in GATE 2020. Um, Belongs to chemical reaction engineering, and I thought that um, this would be a great example to show the various concepts of recycle ratio involved in plug flow reactor calculations. So let's proceed with the problem. So it states that in a lab experiment, a unit pulse input of tracer is given to an ideal plug flow reactor operating at a steady state with a recycle ratio R equals to 1. The exit distribution ET of the tracer at the outer of the reactor is measured. The first four pulses observed at T1, T2, T3 and T4 are shown below. So as you can see, there is a figure at T equals to 0 which shows a singular spike, and it's followed by a plug flow reactor with recycle ratio R equals to 1. There is a residence time distribution function graph versus time, or the excitation function as you might like to call it, which shows four spikes at different times T1 to T4. In addition, we've been given various assumptions used for determining the problem. So it's also given that if the space-time of the plug flow reactor is tau seconds, which one of the following is correct? So the best way to proceed with the problem is to take note of the plug flow reactor with the recycle ratio R in it. So what we'll do is we'll first draw a model of the plug flow reactor. Sorry. Right. So this here is our plug flow reactor. Now in this plug flow reactor, the feed comes in at a volumetric flow rate of V0, and what happens is there is a recycle stream. This here the recycle ratio is set as R for this stream, and the recycle flow rate is V0, R. What happens is as soon as the stream V0 uh, leaves the reactor, it gets separated into two different streams. One will be V0 R and the other will be V0 say dash, and as these two streams meet here, they mix and form a different stream which should be named as say V0 M. Now what we can do is we can look at the definition of R, which has been given in the assumption. It has been told that R is the ratio of the volume of the fluid returned to the entrance of the reactor, the volume leaving the system. So R, as you can see, can be written as V0, R by V0. So let's say this is equation 1 for us, and now here at this particular node or say point, if we do a mass balance, then we get V0 at node 1, V0 equals to V0 plus V0 R equals to V0 M. So from here, equation 1, we get V naught plus R times of V naught equals to V naught comma M, which would give us V naught comma M equals to R plus 1 V naught. So this here is a very important relation that we have derived in this case, which will be used in the future. So now it has been provided that tau is the space time of the reactor. Of the Lacto reactor. So normally how we write tau as? We write tau as V by V naught in ideal case. But now due to this recycle, what happens is this tau gets written as tau dash is equal to V naught. Now since there has been a recycle, so we won't consider this as the we won't consider V naught. We won't consider V naught as the uh, V naught as the flow rate that we write in the denominator. Instead, since we are talking about the fluid that enters the reactor, so we will be talking about V naught M here. Thus, this tau's expression will have a change in the denominator, where V naught will get changed, where this V naught should change to V naught M. Now, from the above relation, that is equation 3, we can write this as V by R plus 1 V naught. This here is our equation 4, and this is the main equation which we will be using for the entire problem. So for T1 we will have tau dash is equal to V by 1 plus 1. Why 1? Because R is equals to 1. So we have V by 2 V naught. Now, and we already know that V by V naught is equal to tau, so it will be tau by 2. Similarly, for T2, we have this tau dash plus tau by 2. Why? Because after this tau by 2 time has elapsed, that is, if we had to explain in a very simple way, we will say that after T1 has elapsed, another T dash gets added to it, because the stream is being recycled. So this would result in this tau dash should result in another tau by 2. We can get this from here actually, so we can directly write this tau by 2, and we already know that T1 is tau by 2, so we have tau. Again, for T3 we have tau dash plus T2. So what we have is tau by 2 plus tau, which is 3 by 2 tau. And for T4 we have tau dash plus T3, which is 3 by 2 tau plus tau. Sorry. What we have is tau dash is always tau by 2, and T3 is 3 by 2 tau, which is equal to 2 tau. So ultimately what we have is tau by 2 for T1, tau for T2, 3 by 2 of tau is T3, and 2 tau is T4. Thus the correct answer would be option B. So option B is the right answer. I hope this answered your query.